Hi everybody, it's Alex. Here to talk about completing the square, a process for solving quadratic equations. Yesterday we talked about factoring, the method of factoring to solve a quadratic equation, which is great, but completing the square is providing an alternative method for doing so. So, right off the bat, let's start with an example of x squared plus 4x plus 4. Well, I know this can be factored. Let's try to go through the process of completing the square using algebra tiles. So, starting off, the goal of using algebra tiles and completing the square is to find an arrangement of the algebra tiles that can be arranged to form a literal square where the side lengths are of equal length. So let's get to it. We have an x squared, so let's use that as our base foundation of our square. Then we have the 4x's to handle. So remember, with algebra tiles and creating algebra tile multiplication, we have a factor of multiplication on the bottom, a factor of multiplication on the side. So we have currently an x and an x. To create the 4x, we'll have to create additional values on top or off to the side. And in order to make a square, we'll need to make sure that there's equal amounts of values off to the side and on top. So let's divide this evenly and put 2x on top and 2x onto the side. That takes care of the 4x's right there. So let's pay attention to the c value. We have 4. We can try to fill in the square by putting 4 in right there. And what do you know? We have a square of equal side lengths of x plus 2 and x plus 2. And that completes the square. So, noticeably, this is represented in the square formation. And that's because this polynomial is known additionally as a perfect square. A perfect square is when you have a factor and you can multiply it by itself, x plus 2 in this example, and x plus 2, and it produces the polynomial. So, perfect squares are also very easy to factor. So let's do an example of completing the square that isn't so easy to factor. So perhaps, let's say, instead of the plus 4 at the end, let's do a minus 1. So there. Which we notice we have the x squared still in our layout. We have the 4x's that we need to divide equally between the side factor and the bottom factor here. So we have the 2x and the 2x's, which are nice. But we have a minus 1, so you gotta get rid of these. Because the plus 2 right here and the plus 2 right there, when you multiply them together, you don't get any negative numbers. So the negative numbers do not belong there. Negative algebra tiles do not belong there. You need to have positive ones. So let's write the negative 1 off to the side for now. That didn't show up very well. Let's rewrite that. There we go. So, a great tool, a great skill set we have with algebra tiles that we learned how to manipulate them is to add 0 pairs. Add 0 pairs to make up for missing features. So, let's do that here so we can fill in the square and complete the perfect square polynomial. This, by the way, is not a perfect square polynomial, but we'll get on to that later. So we add 4 0 pairs in, and the 4 positive components can fill in complete the square. But we must remember to take care of the negative components as well. So we draw 4 more off to the side. So I see a completed perfect square right there. So, step 1 done. We have our representation of a square with algebra tiles. Step 2 would be, if we're using algebra tiles, to try to rewrite this equation representing our picture. So, in order to do that, we'll take this polynomial and rewrite it as shown. So, we have our x squared still. We have our 2x's and two x's on both sides, which total to 4x. And then we have 4 positive units, so plus 4. But then we also have negative 5. Now, while we could combine like terms and put the 4 and 5 back together, that would just get us our original polynomial there, which is not what we want. Instead, we wrote it so that it was separate, because this perfect square right here is represented as an equation right there. And you can rewrite a perfect square polynomial as a factor that is squared. So we have x plus 2 and x plus 2. So let's rewrite that way. We have x plus 2 squared. However, we still have that negative 5 to contend with, so we need to carry that down. So now we have rewritten it so that we have our perfect square in the equation, as opposed to this polynomial where we did not have a perfect square obviously present. So the third step, first step is to create a square representation with algebra tiles. Second step is to rewrite that in an equation form. Third step is to solve the equation. So you do that by setting it all equal to 0 and solving. So you add the 5 across, which will get you an x plus 2 squared is equal to 5. You square root both sides to undo the square, so you have x plus 2 is equal to square root of 5. Though it's important to remember that that is a positive or negative square root of 5 by nature of the square root. Then you subtract the 2 across. We have x is equal to negative 2 plus or minus square root of 5 as its 2 factors, as the 2 solutions. And that is this equation worked out to its fullest, solved by completing the square. So, one important thing about why completing the square is so important is that sometimes you can't always rely on factoring to get the job done. In which case, you can rely on completing the square. The other thing is that no matter what's thrown at you, completing the square will always be able to solve a quadratic equation. It's actually the basis of the quadratic formula, which we'll talk about in the next unit. So, more on that later. So, you might be skeptical. Completing the square can be done for any quadratic equation. We demonstrated that no matter what the c was, we could do it. What about the b term? We were talking about how if you want to get a square representation, you need to have the b term split evenly between the 2 factors, right? So we previously had 2x's up here and 2x's over here, but what if b is an odd number? Dividing by 2 doesn't get you an integer. Well, let's do an example of that. So, x squared plus 3x plus 3x plus 1. So, let's, we have our x squared right here. And then when we try to divide the 3x by 2, splitting it up evenly, we get 3 halves, or 1 1/2. So, we have our 1x right here, but then you have a half x up here. And that's a limitation of an algebra tile. That's the tool algebra tile. You can't have half an x with an algebra tile. However, in mathematics, it is possible, even though you can't represent it with an algebra tile. So, we have 3 1/2 right here, and then similarly, we have to have the other 3 1/2, or not 3 1/2, 3 halves. Then we have to have the other part of b that's equally divided, the other 3 halves, go down to this factor here, which gives you an x and a half x, which you can't really draw. So, half and half. So that's a limitation of the algebra tile drawings. So I think I'm going to drop this picture, not entirely, but for most parts, because it's a limitation. Let's focus on the algebraic representation. So what we just did was we split it into, we tried to create a perfect square by splitting it into a term which is an x plus 3 halves, which is the one useful thing for this drawing, is that it shows what we split our factor into, is x plus 3 halves squared. However, x plus 3 halves, when we do our FOIL method that we talked about the other, throughout this last week, it does not give you this. That's because this isn't a perfect square polynomial. But we can modify it, like we did with the -1 example. So when we FOIL this out, we get x squared plus 3x plus 3 halves squared, which is 9/4. So our first term matches up, our second term matches up, our third term does not. So, how do we adjust this equation? How did we adjust this? How do we adjust our equation that we're our perfect square to match our old equation? Well, we need to figure out how much of the c value we stole to go into that, which was we have 9/4 there. So instead of 9/4, what we need to do is we had to also subtract 5/4. So, because 9/4 minus 5/4 will get you the one that we need in our original equation. So, instead of writing it like this, we take the minus 5/4 on up to our perfect square, and that is how you complete the square with an odd b. It doesn't look as nice just because you have some rational numbers, but it still works. Still might be skeptical, just because even though we have proven that for any c or any b, you still might think that there's an a value that could change, so that completing the square with an a value might not work. Let's talk about that very briefly. So, instead, let's say we have an example of 2x squared plus 6x plus 5. So, first things first, this quadratic equation is equal to 0. In order to complete the square, you do want the coefficient equal to 1, and you do that by dividing by 2. And then, well, it's really dividing everything by 2, and then you divide that side by 2. The result of that would get you x squared plus 3x plus 5/2. Which gets us this very similar problem to the one that we just had. Because we have an odd b, which would require splitting that b in half in order to find our perfect square factor. So we have our x plus 3/2 as our perfect square factor again. However, that can be rewritten as x squared plus 3x plus 9/4, as we know from the last example, which doesn't quite match up to this again. And it's the same process as last example, because what do we need to do to the c term here to match it from our original equation? We have to do, that's 10/4, this is 9/4, we just have to say plus 1/4. We bump that back up to this, and we have our square completed. I mean, we can still, well, we have our complete the square steps done, but we need to still solve for the quadratic equation. So, when you have x plus 3/2 squared plus 1/4 is equal to 0, you have x plus 3/2 squared is equal to negative 1/4 when you subtract it across. You do the square root across. You do the square root to undo the square. So you have x plus 3/2 is equal to square root of 1/4, which is 1/2. Well, positive or negative 1/2, keep that in mind. So then you have to subtract the 3/2 across to solve for your x. So you have x is equal to negative 3/2 plus or minus half. So your x solutions are going to be either 2, nope, either negative 2 if you were to subtract it, or negative 1 if you were to add it. And that is how you complete the square if your a value is not 1. So, to wrap this up, we have completing the square is a method that can be done for any quadratic equation, and it can be used even when you can't factor. And for future reference, it's going to be used for the vertex form of a quadratic graph. So it can be revealed, it informs you where the vertex of any quadratic function is, but that's another lesson. So until next time.